Okay, so let's recall what the zeta function is. The zeta function, you have some positive, you have some number bigger than 1. You define zeta to be the sum of, from n equals 1 to infinity, of 1 over n to the s. Right? And the point is that, you'll notice is that this converges. Right? And why does it converge? Because s is bigger than 1. Right? Because s is bigger than 1. Right? So if you want, you can compare it. You can compare this 1 over n to the s to 1 over x to the s. Right? For x bigger than 1. This integral's convergence, this sum's convergence is equivalent to this integral's convergence, right, by the integral test. And since s is bigger than 1, this thing converges. Okay, so then we have this thing called Euler's product formula. Says, okay, well, again, let s be bigger than 1, and let p be the collection of primes. I'm using this fancy looking p in the notes. I hope you like this p. Anyway, this is actually the p from something called the Weierstrass A function. In complex analysis. So this is actually an improper use of this p. One should not use this p, except for the Weierstrass K function. Okay, but I'm going to use it. So let p denote the collection of primes. Then the zeta function can be expressed as an infinite product. 1 over 1 minus p of s. P. And maybe you see the intuition here, right? This 1 over 1 minus p to the minus s. This thing is, what is this? This is the sum of a geometric series. Right? What geometric series is it? This one, right? P to the s, p to the 2s, p to the 3s, etc., etc. P to the minus, p to the minus. Yeah, that's right. P to the minus s, blah, blah, blah. Right. And so we're taking the product of all these geometric series, right? If you think about it, what we're going to get is, right, if you take one element from each of these products, right, then you're going to get, by the fundamental theorem of arithmetic, you're going to recover all the integers, all the positive integers, right, to the s. So that's the idea here. Right. So here's the. Here's the proof. So that and the natural number, and consider the sum 1 over n to the s, and this from 1 to n. Now pick any n bigger than n, right? And you realize that all of these guys, each of this 1 to n has a prime factorization. terms of primes less than n, in terms of primes less than n, and primes p less than n, where p occurs fewer than m times. So what we get is that the sum, this partial sum, then is controlled by this this product 1 over p minus. Okay, this is the key part. So this I hope people understand this thing. Right. Right, we're taking primes. So p. We're taking the primes less than n, right? And we're taking these partial geometric. We're taking these geometric sums up to the nth power of p, right? Okay. And when you multiply these things together, well, you're going to get all the integers. Right? You're going to get integers where there are factors of p of greatest p to the m, right? And the primes are all less than n. Right? Well, all of these n are such integers, so we get something that's bigger than this. And then from there you say, well, look, this is smaller than taking the product of the full geometric series. Taking the product of the full geometric series, right? Right. And then letting n go to infinity basically gives you that infinity gives us that that the zeta function is bounded above by this thing. Right? So the product of does it make sense? Right, and then the opposite direction is basically is pretty similar. So I'm going to okay. So this thing is Euler's product formula. Put it in here. This is pretty cool. I hope you like it. Sort of strangely, one thing we can do with it is to show that that there are an infinite number of primes. So theorem, Euler's theorem, infinitude of primes. So this is due to and it's this fact that 1 over p prime divergence. Okay. Because if they were just a finite number of primes, then this would of course converge. So this is Euler's version of Euclid's fact. So we're going to use the product formula, and we're also going to use a lemma about the logarithm that the natural log of 1 plus x for x smaller than a half, the natural log of 1 plus x equals x plus something, where that something is smaller than x squared. And this is basically done by power series expansion. You just take the power series expansion about there, and then you see that as long as x is less than half, then the thing is bounded by x squared. Okay. So let's do the proof of does anyone want to see this thing? The power series expansion? No. So let's do the proof of the infinitude of primes. So you say, well, okay. So by Euler's formula, Zeta s is this thing. So if we take the natural log of it, we get the sum sum. And then using the lemma, well, natural log of zeta s is this negative 1 over p to the s plus this thing, which is of the order of p to the 2s, over p to the 2s, right? The square of this thing. I think you're found it. Why you found it?
Yes, can't we make 1 minus 1 p to the s not have absolute value smaller than half? Or sufficiently large p?
Yes.
Well, don't we look at I thought the proof they looked at the tail no matter how, so you move that
Oh,
out.
no, that's a bad idea. I retract it.
Okay, yeah. Yeah, no. So. Okay. Right. Okay. And then we say, okay, well, this is that's something of the order of 1. So what's wrong with this? So here's what is written in the book. I say, well, look, summation 1 over p to the 2s is actually smaller than 1 over n if you take all the primes, right, it's going to be smaller than summing these guys. Right? And this converges. Right? This converges to some number, so it's a constant. Right? So you say that this thing is the sum of things of the order of y is order of 1. This is actually not, I mean, it's not completely right, but it's just an error in notation, right? So right? Each of these guys is of the order of 1 over p to the 2s, which means that they're bounded by some constant. Right? Each is bounded by some constant times 1 over p to the 2s. That constant could be different, right? So it's not quite right to say that you sum these guys of this order and you get something of this order. Okay. But rather, if we look at the lemma, it's not just order of p squared. It's controlled by p squared, right? So we know that we just write it like this in some p of 1 over p to the s. Right? And each of those guys, right, each sum of these guys in absolute value is controlled by this, which is controlled by this, which is constant. So there's just a slight this writing. In any case, we get some constant. So that is to say that if we look at this thing, 1 over p to the s, p and p, then it's natural log of this thing and minus some constant. So let's hold that in mind for now. Okay. So right. Okay, so now consider right, remember what we're trying to get. We're trying to say something about the sum of 1 over p, where p is a prime. Right? Okay, and we have this thing about 1 over p to the s. Right? So let's look at what happens to the right-hand side as s tends towards 1. Right? So consider the limit of the right-hand side. Right? As s tends towards 1 from above. Okay. So the limit, just by definition, it's the sum, right? And it's that's bigger than the limit of the partial sum. N from 1 to n. Sorry, there should not be a log. This is bigger than this, and as s tends towards 1 from above, for this thing just tends to 1 over n. So what you see is that the limit of the zeta function as s tends to 1 from above is bounded below by the partial sum of the harmonic series, right? For every m, right? So we see that this limit is infinite. Right? So this thing is infinite. And since the lim inf of this thing is infinite, right? If we take the lim inf of this, so if we look at summation 1 over p, right? This is the thing we're trying to show. We're trying to show this thing is infinite. Well, this is bigger than the lim inf. As s tends to 1 from above, 1 summation 1 over p of the s, right? which is bigger than the limit of that thing, which is infinite. Limit of zeta is 0 comes to 1 above. It's constant, it's infinite. So that gives us Euler's proof of the infinitude of primes. I mean, something much better than the infinitude of primes. But if you thin out the harmonic series to just the primes, then that thing still diverges. Okay. Any questions? Why do we use the log? Okay, so if you read the text, you know that it's this fact, this proof that inspired Dirichlet. Right? So Dirichlet says, okay, right, we want to show that we want to show this conjecture of Legendre that there are infinitely many primes of the form P is congruent to L on Q, right, where P of Q P where, sorry, but Q and L are relatively prime. Sorry. Q and L are relatively prime. So Dirichlet says, well, let's play the same game. Let's show that something of this form, where P ranges in the primes and P is congruent to L on Q. Let's do the same thing. Let's just sum, instead of summing over all primes, let's sum over all primes that are congruent to L on Q. And so, so the first thing that we're going to do is reduce this problem. So we're going to reduce this problem to a slightly simpler problem. And we're going to do it using a kind of Fourier inversion formula on Z on the group of integers Z star Q. So let G be Z star Q. And so it's the units, as we call, it's the units of remember, right, if A is a unit, right? If A in here is invertible, there exists some x in ZQ such that xa is congruent to 1 mod Q. Right? Of course, that's what I. Right. So, wondering what the set of units is. Right? If you think about what invertibility means that there's some number, you multiply it, you get 1. Right? But that's the same thing as saying that the greatest common divisor of A and Q is 1. Right? Because some XA plus YQ is equal to 1. And so the greatest common divisor is 1. So what the set of units is, of course, is the set of numbers in Z mod Q that are relatively prime to relatively prime to Q. So, so this is the set that we're going to be doing our Fourier analysis on. So, just for notation's sake, let's define the Euler P function. It just records the number of integers relatively prime Q. So it's defined to be the size of the set of units of ZQ. Right? So it's the number of integers between 1 and Q, between 0 and Q, such that N and Q are relatively prime. Sorry to just put up definition after definition, but it will just wait a minute and then we'll actually do some math. Okay, let deltas of L be the characteristic function. This thing be the characteristic function of the set of L, right? So L is some, right? L is some element, L is some unit here, right? And you let this guy be the characteristic function. So it's it'll give you 1 if n equals L, and give you 0 if it is. So, sorry, okay, sorry, so let me try and give you some sense of what we're doing, because I think this is, I'm just going, I feel like I'm being that professor who just puts, definition after definition. Okay, so what what we're going to try to do is right, we're trying to we're trying to get control of this thing, right? P to the S. P and P with P common with L and Q. Right? Here's what we're trying to get control of. Right? And what we're going to do is we'll actually look at at this guy, whatever P to the S, right? Where P is S is yes, and we'll take the limit as S goes to 1, just like we did in the previous case. What we're going to do is basically recognize this thing as a sum of this form. Okay, over the same sum. So P to the S. So we're going to take we're going to recognize this thing as a sum of characteristic functions, basically. Okay, and then we'll take this thing, we'll take these characteristic functions, and we'll do the Fourier inversion on them. Okay. That Fourier inversion will express each of these sums in terms of the characters of Z star Q. Okay, and then from there, it'll turn out that we'll break it up into two parts. One of those things will be infinite. Okay. One of those things will be infinite, and then the other part. So one of those things will be infinite, and so the problem will then be reduced. What's the reduction? The problem will be reduced to showing that the other part is finite, right? Because if the other part is finite, then it's not going to affect the magnitude being infinite. Okay, so that will be the reduction of the problem. Okay, so now I feel like I'm actually talking. Okay. So yeah, I have to say that every once in a while as a teacher, I fall into like a great mood of depression. Like you're in the middle of a lecture and you're like, oh, what's the point of all this? And you just feel like running out the door. Then you have to remind yourself, okay, there actually is a point to this. What's the point? We're actually doing something actually really well. So the point is to understand these characteristic functions. Okay? So these characteristic functions are the characteristic functions of single points, okay? Single units. It says, do you hit the unit? Yes. If not, then no. Okay. You have these characteristic functions, and you extend them. Extend these of L to all of Z, ZQ, and all of Z by just defining it to be 0, right? By letting delta L be 0 on the non-units. Okay. So it's just 0 everywhere except at L. And then you extend it to all of Z. We're going to do the same thing with characters. So let E and G hat be a character. Right, character G, and G was this group. We define the Dirichlet character extending E by I of M is going to be e to the m, e of m, if m and q are relatively prime and 0 elements. So all this is saying is that we extend this guy periodically. Right? No, it's not. No, we extend it periodically. Okay, so and just notation, let x naught denote the extension of the trivial character. Okay, and so here's the lemma that's going to be achieved. That the extension of the characteristic function can be expressed as 1 over phi of q, and the size of the group times chi L bar chi M, where chi ranges over all the Dirichlet characters. Right? So if you want, you can think of this as each of these chi's is chi's of E, and E is going to range over the group of characters. Like each chi is an extension of some E, some character. Okay, and what this is, of course, is just an extension of the Fourier inversion formula. Right? It's just an alternate expression of the Fourier inversion. So consider the Fourier coefficients of deltas of L on G. Right? What are they? Deltas of L, evaluated at some character, of course, is 1 over G summation delta L. em bar and G. This is the Fourier. This is how you calculate the Fourier coefficients. Right? But you notice, of course, that delta L is going to give you 0, except when m is equal to L. Right? So this is 1 over G times E L bar. Right? And then by the Fourier inversion formula, Fourier inversion says that delta at some point, right, is going to be a summation of the Fourier coefficients times the characters, right, evaluated at that point. As E ranges over the characters. Well, that is just whatever size of G is calculated, EL bar EM as E is G hat. Right, and then this formula is just that formula extended to all of Z. Right? So extend the definitions of delta and E to all of Z. Right? And you get this thing. So this thing, right, expressing this in terms of the characters is just the Fourier inversion formula. Okay, so So, so now let's reduce the problem. Now let's reduce the problem. Considering this sum, right, where P is conjugate to L mod Q. And we can express it as we express it like this in terms of the characteristic functions. Is that right? Sorry. Something is following up. Is this right? This is going to be, let me think for a second. So this is equal to 1 if P is conjugate to L mod Q and 0 otherwise. Okay. Right, so, actually, sorry, it's not right. I'm glad I'm actually sane. I'm going to take the sum of all primes. Okay. Now it's right. Right, so we express this thing as a sum of these characteristic functions. Okay. And then, of course, we're going to use the Fourier inversion formula. Right? And we write this thing as 1 over theta q summation xl bar summation xp qds as chi ranges over all Dirichlet characters and is p here. Right? Okay.
So obviously, I can change the order.
I'm sorry?
So obviously, I can change the order of the summation.
Let me think. So we've got the sum of those guys. Those guys are finite, right? Right. There's only a finite number of characters, right? So that should be okay. Okay. And so we split this thing into two parts. We split it into two sums, one where the character is the trivial character, and one where the character is the non-trivial, our non-trivial characters. We write 1 over this times the trivial character. The trivial character is going to give us just 1, right? So so this gives us, we get the sum S. So P prime where P doesn't divide Q, okay, plus this other thing. Right. And then we say, okay, well, this first thing, we're taking the sum over. We're taking the sum over p's that don't divide q, and there are only finitely many primes that don't divide q, and so this thing is infinite. This thing is infinite. And so the problem reduces to showing that this thing is finite. So the problem reduces to this one, to show that if I is any non-trivial Dirichlet character, then summation I P or PDS is bounded as tends to infinity. So we'll prove something stronger, that each of these sums is actually bounded. We've kind of find it